Hey, what's up, guys? It's Sheng here. So this time, LeetCode number 1993, operations on tree. So this one is a design problem. So basically, you're given like a tree with n nodes, right, from 0 to n minus 1, and then in the form of a parent array, where like the value of this parent I is the parent of the ith node, right? So the root is 0, so the parent 0 is always minus 1. Okay, and then you need to implement three operations. First one to lock. Okay, so you will basically lock the node with this current user, right? And you can only lock if the node if the if the un, if the lock a node of is unlocked. Okay, and then unlock, right? Similarly, uh, you may only unlock a node if it is currently locked by the same user, right? Or if the lock is unlocked, then also failed, right? And then you have this upgrade. So this upgrade is a little bit more complicated, where in order to upgrade a node, so you have to meet all three conditions. The first one, this current node is unlocked, right? And then second one is it has at least one locked descendant by any user. Doesn't have to be by this current user, right? And then the third one is that it doesn't have any locked ancestors or locked parents, right? So that's it, right? That's the basic idea, and then we have an example here. I'm not going to go through this one; it's pretty long. And the constraints are like 2,000, right? And then most 2,000 calls will be made. Okay. So obviously, the for lock and unlock is pretty easy. All we need is just to create like array, right? Array with the length of the tree, right? And then basically the value of the array will be the user who locks that, right? And then for the upgrade, right? For the upgrade, this one is easy to check, right? Since we have the array, and the last one is also easy to check because since the tree is given in the form of the parent, right? We can simply just use this parent array to traverse all the way to the top to check if there's any parent that is locked. Okay, and this one, right, is the little bit hard, more difficult to check because this one we need to check the children, basically the descendants. But since we're only given like this one, right, of parent form, we cannot traverse down. So which means we have to, when we initialize this class here, we also need to build the tree, basically build the regular tree from top down, so that we can traverse it back, right? Traverse it down. Yeah, I think that's it for this one. Nothing too fancy. For this problem, it's just a little bit of implementation heavy, right? I mean, I made a few mistakes, while implementing this one. And let's start doing it. Let's do it. Let's see. Um, cool. So first one is this. Okay, we need the self.locks, right? So the first one is the locks. At the beginning, everything is 0, right, with the length of the parent, right? So that's everything we have, the locks. So the reason we can use 0 is because the user, right? So the user starting from 1. So 0 means it's not locked, right? Anything that's greater than 0, it means that this node has been locked, okay? And then we have a parent, okay, equals to parent, right? And then we need to what? We need to build like this kind of regular tree, right? So how can we build a regular tree? So first we need a node class, right? So for me, I use this another class to represent the node. Okay, so it's going to be a self.value, right? And then we have two properties. The first one is the value. Second one is the children, right? Children of array, because we could have multiple childrens, right? It doesn't have to be a left and right. Okay, and then to build this tree, right? So it so the order is not guaranteed, right? So we could have been given the parent first and then the child later, right? That's why we need to make like another nodes dictionary, right? For us to save the node we have seen before, so that later on when we see the same node, we can just get the previously created node from this dictionary instead of creating a new one. Okay, and then the node 0, right? So basically the key will be the key is the node ID, right? Value is the node itself. Okay. So to begin with, right, we have the node 0 equals to node 0, right? And then now we're traversing the rest of the nodes from 1 to n, right? So we have a value, it's going to be I, and the parent, it's going to be a parent of I, right? That's what we have. We have a value and we have a parent. So for what we need to do first, we need to check if either of those has already been created before, right? So basically, if p not in the self dot nodes, right? We do a self dot nodes p. If not, we do what? We create this parent node, right? And then after that, we have parent node equals to the self dot nodes p, right? Similarly, for this value, right? We need to do the same thing. If the value not in the self dot nodes, right? We do self dot nodes dot value equals to the node of value. Okay, and then here we have current node equals to self dot nodes dot value, right? And then only thing left is parent node dot children, right? Dot append current node, right? So this part is make sure we're utilizing the existing node if it's already created, right? And then we just append this one to that. So now we have the tree created for us. Okay, and then we can implement this three functions here. So the lock and unlock is pretty straightforward. Basically, if the self dot locks dot number is greater than 0, right, then we return false. Okay, because it's already been locked, right? Otherwise, we lock it, right? Self locks dot number equals to user, right, and then return true, right? Similarly for the unlock. So for the unlock, we need to check two things. First, if this one is equal to 0, it means that it's already locked. Or if it's locked, but the person who locks it is a different person. Okay. Right. Then we return false. And then self dot locks number equals to 0, right? And then return true. Okay. And for the upgrade, right? For upgrade, basically we just check these three conditions one by one, right? So first we check if this lock has already, if it's not locked, if it's locked already, okay, right? Then we return false, right? Second, we check if any ancestor is locked, okay? So we have a parent, right? Parent equals to number, and then we have a flag. So it has ancestor locked equals to false, right? So I do this while true parent is going to be the self dot parent dot parent, okay? Um, I think we can do something better because so the reason if we have a while true here, the parent when we have the new parent, we'll check. Basically, we'll check. So this is what we'll check: if the self dot logs, right, dot parent is greater than 0, right, and then basically we'll set this one to true, right, to true, and then we'll break. But the issue is that so this parent could be -1 because remember the root node has a parent equals to -1, right? And if the parent is -1, then this one is it's wrong basically, right? So basically it means that we don't want to continue if the next one is a root node, right? So that's why we can do, instead of while true here, we can check this. So basically if this one is not -1, right? Basically if the current one is the next one is -1, then we stop, right? Otherwise we check this. Okay, and then so if has this one, right, and then return false, right? Basically this one we check ancestor, right? And then here we check descendant, right? Let's check descendants. So to check descendants, we can do this, right? We can simply check the so we have current node. So we have current. Let's get current node first. It's going to be self dot node dot number, right? And then we just use DFS, right? Not DFS. The iterative DFS. I'm going to use a stack. Okay. It's going to be the children of node for a node, right? In current node dot children, right? So to begin with, we have this stack, and then we need another flag has logged descendant, okay, equals to false, right? While stack current is going to be the stack dot pop, right? And then if self dot logs of current dot value, remember, so this one is current node actually, so yeah, this one is current node. It's not this one is current node. This one is also current node, right? It's not like the index, right? It's a node itself. That's why we have to do a node dot value to get the node ID. So if this one is greater than 0, right, and then we do it has logged descendant equals to true, right, and then we break. Otherwise, stack dot extend, right, current dot children, right, and then similarly we check in the end if there's no logged if there's no logged descendant, we return false. Okay, so if everything passed, now we can update, perform update, right? First step is to log the current node, right? Logs dot number equals to user, and the second one unlock, right? The unlock all descendant, right? So we do a similar thing basically, right? We just copy and paste this one, right? The only difference is that here every time we just set update, right? We'll update this one to be 0. Okay, and then in the end return, oops, return true, right? So that, I think that's it. Yeah, let me run the code. Invalid. Oh, define. Did I? Oh, maybe a space. Okay, yeah. '82. Self logs current dot value equals to 0. Oh, 1 to n. Oh, is it? Did I? Fine. Okay, let me define the parent here. The length. Okay. PAR. Yeah. A lot of typos. Yeah, line 77. Oh my god, so many self. Okay. Okay, finally. Submit, right? Okay, cool. It works, right? I mean, nothing too fancy, right? I mean, unsquare time complexity, right? Because we have upgrade here. Upgrade, we have while loop, and while loop, but still O of n, right? That's why it's unsquare time complexity. Yeah, I think that's it, right? As you guys can see, nothing too fancy. It's just like we just need to build like a regular tree based on the parent, right? So that we can basically traverse down. And that's it. Cool. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.